What is the point of physics? Why do we need it? What's it trying to accomplish? Does the study of physics have a goal? The obvious answer is to explain the behavior of the universe and the things in it. What is the universe and what exactly is in it? Those are empirical questions for the scientist. But what do we mean by explanation? That is a question for the philosopher. Our questions in this lecture are, what is an explanation? What makes some explanations scientific? And does physics actually explain anything? The first philosopher to wrestle with these questions was Aristotle. He explicitly says that the purpose of science is to set out the causes of natural phenomena. Recall from our first lecture that Aristotle points out that the word cause is ambiguous. It has more than one meaning. Indeed, he famously says that the word cause has 4 completely different meanings. If one were to come across a statue and ask, what's the cause of this work of art? One could be asking any one of 4 questions, and thereby could be rightly given any one of 4 answers. There's the material cause for the statue. That is, why is there a statue here instead of nothing? The answer is the marble of which the statue is composed. Take away the material that makes it up, and you take away the thing. Hence, the matter is one cause for the thing it comprises. This is the material cause. But why is it this statue? The answer is the shape. If it had a different form, then it wouldn't be the statue that it is, but a different one. The form of the thing causes it to be what it is. This is the formal cause. Now, these may seem like silly answers to the causal question beneath the level of scientific explanation. But consider the sorts of explanations we might give for questions about chemistry. What's the cause of a diamond? In one sense, we answer this with Aristotle's material cause. Carbon atoms are what make it up, and so carbon atoms cause there to be a diamond. But why is it a diamond and not a lump of coal or graphite? Because of the pyramidal arrangement of the carbon atoms bonded to each other. It's the geometry of the matter that causes it to be the diamond it is. Stereochemistry, the study of the geometry of atoms in molecules and the effects that has on chemical properties, answers scientific questions by making use of Aristotle's notion of formal cause. The third notion of cause that Aristotle employs is that of efficient cause. This is what we usually mean when we ask what caused something. It's the process by which something was brought about. For the statue, the efficient cause was the chiseling of the artist. When we want a causal explanation, what we're usually asking for is to be told the story of the relevant happenings by which the thing came about. This, again, is the efficient cause. The final cause for Aristotle is indeed the final cause. The final cause is the purpose the thing serves. It's that for the sake of which a thing was brought about. If we ask for the final cause of a statue, it might be to worship the god depicted. It might be the making of money by a commissioned artist. It might be the artist's desire to demonstrate his skills in depicting reality. In this case, the causal answer to the why question is a person's intention or desire. If the manager of a restaurant walks into the kitchen to find the cook throwing ingredients on the floor instead of cooking, he might ask his employee to explain himself. If the cook's response was, well, first my mom met my dad and they fell in love. Then they got married, and then that night the manager would stop him right there for a couple of reasons. One being that he was asking for the final cause of the cook's actions in the restaurant kitchen, not the efficient cause of the cook's being. I don't want to know why you are, I want to know why you are doing what you're doing. Final cause makes sense whenever we're dealing with individuals to whom we attribute free will. To explain human behavior, we need to account for volition. What is the end which this act was intended to serve? But for Aristotle, that question also makes sense in physics. Like most Greek thinkers of his period, Aristotle bought into the view we call teleology. The term comes from 2 Greek words, telos, meaning end, aim, or goal, and logos, which means word, concept, or logic. Put the two together and you get teleology, which is the view that all things possess a purpose. Everything happens to serve a plan or as a cog in a larger machine that itself has a purpose. Aristotle held that all things possess a telos. An artifact, something that's created by people, has its telos imposed on it from outside. But natural things have their teloi naturally built into them. And every natural thing on every level has a telos. In contemporary evolutionary biology, for example, we commonly give teleological explanations. Why do humans have an appendix? We'll consider what function it served our ancestors and how it came to be in order to make a difference in terms of natural selection. But Aristotle held that physics as well requires teleological explanations. Why did a rock fall? The material cause is that which makes up the rock, which is a combination of the earthly elements, earth, water, air, and fire. The rock is made of earth. Earth has a natural place, the center of the universe. When you remove a thing made of earth and place it in the air, it's not where it belongs. It has a desire to return to its natural place. So when you let go of the rock, it will, for internal reasons, seek its natural place. It has a goal. It wants to be at rest in its natural place. So Aristotle doesn't appeal to an external force like gravitation in explaining the falling of a rock. Its motion derives from itself, just as your motion getting up to get a drink of water derives from your own will. The teleological presupposition leads to a basis for physical explanation. What is the rock seeking to do in falling? This may seem silly to us, but consider seemingly similar statements in contemporary physics. Hey, there's a thunderstorm out there. Don't walk around holding that metal rod over your head. Don't you know that electricity seeks the path of least resistance? Is this just metaphorical? Or is there still a teleological component to the structure and behavior of the material universe? What kinds of explanations ought we give in physics? This question became a point of serious contention in the 17th century. René Descartes proposed what was called the mechanical philosophy as a foundation to physics. All material happenings were to be explained in terms of material interaction. Only pushes and pulls of things against things could be posited as explanations for motion. Why did that chair move? I pushed it. Seems to make sense. But then there's the problem of the motion of planets around the sun. What purely mechanical explanation could there be for that? To fix this problem, Descartes made space into matter. Space is stuff, and stuff can push stuff. Consider a bathtub with the drain plug pulled out. Now, around the drain will be a vortex of water, and if, say, a hair was floating in the water, it would get pulled by the water around, and then down the drain. In the same way, matter in space caused vortices in the space stuff, which dragged objects far away, like planets, around the sun, and close by objects, like apples, straight down to the earth. By making space into a material object that could interact with other material objects, he was able to provide a completely mechanical explanation for gravitational phenomena. Descartes' physical theory of gravitation and his mechanical philosophy were replaced a few decades later by Isaac Newton with a new theory of gravitation. That theory posited a gravitational force between any two massive objects that operates along the line connecting their centers of mass and is proportional to the product of the masses and inversely proportional to the square of the distance. Gravity is a force across space, generated by the mass of the object, and there is an incredibly accurate formula to describe behavior as a result of it. Once gravity became a force between objects, there was no need for space to play any operational role other than to give an amount to the distance. Hence, according to Newton, Space was not a material object, but an underlying three-dimensional piece of graph paper that gives every object an absolute address in the universal neighborhood. Objects were in space, but space in no way affected the objects. It was a force between them that caused the motion. Cartesians were apoplectic about this new theory, not only because it challenged the physics of Descartes, but because it challenged the metaphysics of Descartes. Newton was proposing what we call action at a distance. If two objects are connected by a rope, then it makes sense how one could pull on the other. Consider a game of tug of war. But you can't have a tug of war if there is no rope. Separate the teams by several meters and just have them try to pull each other by generating a force? Absurd. But that absurdity is the central mechanism by which Newton says the entire universe operates. They demanded of Newton that he explain gravity, that he show us the mechanism, that he demonstrate how the earth can pull on the apple if there's no string connecting them. Newton's response was, hypotheses non fingo. I frame no hypotheses. I do not know how the underlying force operates. I only know that this is the equation by which it's accurately described, and it may be used to predict or account for the motion of the planets, the tides, the bulging of the Earth at the equator, the appearance of comets, so much more. Newton provided an account of the phenomena, that is, a mathematical structure which describes their behavior and interaction, but did his theory provide an explanation for them? If we don't know the mechanism by which the pull is pulled, has Newton's theory of gravitation and mechanics explained why the planets move in an ellipse, why the Earth is flat at the poles and bulging in the middle? Has it explained anything, or has it just predicted or retrodicted it? Newton himself thought that his theory did not explain anything. There was a cause, but it wasn't a physical cause. Newton despised Descartes' mechanical philosophy because to require all interactions to be completely determined by pushes and pulls of matter on matter left no room for God in the regular activity of the universe. God is the explanation. The universe is God's creation, and he operates it according to his will. So no, the theory itself does not explain the working of the universe, but when combined with his theology, it does. Explanation, Newton thought, requires an appeal to metaphysics. Physics itself is not enough to generate an explanation. And that's our question. Is physics itself enough to generate explanations? Can physics, bare physics, explain? Bertrand Russell, at the beginning of the 20th century, thought that Newton had gotten it half right. In a paper he wrote in 1912 entitled On the Notion of Cause, Russell tries to remedy the situation. Because I love them so much, allow me to read the first two paragraphs of the paper. In the following paper, I wish, first, to maintain that the word cause is so inextricably bound up with misleading associations as to make its complete extrusion from the philosophical vocabulary desirable. Secondly, to inquire what principle, if any, is employed in science in place of the supposed law of causality, which philosophers imagine to be employed. Thirdly, to exhibit certain confusions, especially in regard to teleology and determinism, which appear to me to be connected with erroneous motion as to causality. All philosophers of every school imagine that causation is one of the fundamental axioms or postulates of science. Yet, oddly enough, in advanced sciences, such as gravitational astronomy, the word cause never occurs. The law of causality, I believe, like much that passes muster amongst philosophers, is a relic of a bygone age, surviving, like the monarchy, only because it is erroneously supposed to do no harm. Classic Russell. Isn't that wonderful? He's arguing that there are no causes in nature. Newton was right to separate cause from physics, but wrong to incorporate it into theology. The famous atheistic Russell wants to finish the job by removing all teleological notions from science. Think of the situation in the way that it was laid out by the 18th century Scottish philosopher David Hume. We have two events, A and B. We can say that A then B, that's no problem because that's open to direct observation. But to say that A causes B is to say something else entirely. It's to posit a third thing, what Hume calls the causal nexus. And that is something we don't observe. We see A and we see B, but we never see the causing. How do we know that there is a causing if we can't directly observe it? Yet, Hume says, we do seem to believe that we can know that the causal nexus exists in some cases and not others. Some things just come after other things, and some things come because of other things. Hume's question was, how do we know when there is causation? Russell's question is one step more fundamental. Is there causation? And he argues in the negative. I will grant, Russell says, that every time a rock hits a window at a certain speed, the window breaks. There is absolutely a correlation there. But no matter how he tries to work out the meaning of cause, it leads to nonsense. For example, consider the problems of causation and time. We know that the time series is densely packed. That is, between any two instants of time, no matter how close together, there's always another instant of time. For A to cause B, B has to come directly out of A in time. That is, they would have to have been contiguous, right next to each other in time. But no events can be right next to each other, as there's always a time gap between them, since between any two instants in time, there are always more instants of time. Indeed, an infinite amount. Furthermore, event A must have existed for some time span, and event B must have existed for some time span. That means whatever was happening at the beginning of the A time period would have to be causally ineffective, and the end of the B time period would be unreachable. So, all of A couldn't be the cause, and all of B could not be caused. Russell tries repeatedly to take the common sense understanding of cause and work it out rigorously. Each time problems like these surface, the whole notion, he argues, seems to be desired because we just can't give up our desire to achieve the sort of explanation that we can get from a person who can explain her intention in setting things up a certain way. We want nature to have an intelligently expressed will. The search for causes in nature is just an attempt, as Newton made explicit, to put God in the working of the world. It's a theological after effect, a remnant left in science. He argues the entire concept of cause in physics is antiquated and obsolete. What replaces it? The law of gravitation will illustrate what occurs in any advanced science. In the motions of mutually gravitating bodies, there is nothing that can be called a cause and nothing that can be called an effect. There is merely a formula. Certain differential equations can be found which hold for every particle of a system and which, given the configuration and velocities at one instant or the configurations at two instants, render the configuration at any other earlier or later instant theoretically calculable. We have to jettison the notion of cause and effect. But what remains are formulas, differential equations, what we hope to call laws. What followed as an attempt to reconstruct the notion of physical explanation after Russell was the casting of explanation in terms purely of the relations of observed phenomena and laws. The big name in this project was Hempel. The German philosopher Carl Gustav Hempel, who preferred the name Peter, had to flee Germany in the build-up to the Third Reich, in part because he was Jewish. He had been the star student of Hans Reichenbach, the head of the Berlin Circle of Logical Empiricists. When Rudolf Carnap, the head of the Circle of Logical Positivists in Vienna, received a fellowship to come to the University of Chicago, there was money for 2 assistants. Knowing the political situation was even worse in Germany than it was at the time in Austria, Carnap wrote to Reichenbach and said to send along his 2 best to go to America where they would be safe. Reichenbach sent Hempel as one of those 2, and he was able to avoid the clutches of the Nazis. Not all of his colleagues were so fortunate. In his work on explanation in physics, Hempel gives much credit to his friend and colleague Kurt Grelling, who, along with his wife, perished in Auschwitz. But Hempel did get out. He taught at a number of schools, most prominently at Princeton. For several years, I conducted oral history interviews with people who knew the early 20th century major figures in philosophy of science, widows, children, students, colleagues. To a person, whenever I mentioned the name Hempel, eyes lit up. He was universally beloved. One former student, now a famous philosopher of science in his own right, said of Hempel that he was the only saint we have in philosophy. Others told me that their families contemplated moving across the country just to live near the Hempels. Princeton has a famously unruly philosophy department staffed by some of the greatest minds who constantly bicker because each believes him or herself to be the smartest person in the room. It was told to me that one of the most famous of them said that the only period of calm in the department lasted during Hempel's tenure there because one was simply too embarrassed to misbehave in front of him. He was renowned as a playful and kind person who wrote great philosophy. Hempel had 2 models of explanation in physics: the deductive nomological, or DN model, and the inductive statistical, or IS models. We'll look at the DN model in detail and show how the IS is a sort of special case of it. Deductive nomological sounds complicated, but it's really not. Deductive just refers to a type of logic, the type where the conclusion necessarily follows from the premises. Consider the classic example. All Greeks are mortal, Socrates is a Greek, therefore Socrates is mortal. This is a deductive argument. If the 2 premises are true, that is, all Greeks are in fact mortal, and if Socrates is in fact Greek, then it cannot be false that Socrates is mortal. Deduction gives us absolute confidence in the truth of its conclusions. Nomological is just a fancy word for being related to a law of nature. The term nomological says to us that we'll follow Bertrand Russell's idea that there are these general equations that govern the universe. According to the deductive nomological account of scientific explanation for physics, an observed phenomenon is explained if we can derive deductively its occurrence from a law of nature. What explains the falling of a given apple? Newton's law of gravitation. Why? Because given the law and a set of sentences describing the observable situation before the apple fell, the apple's falling is a necessary consequence of the law. The law covers the instance, so the law explains the instance. If you asked, why did that apple fall? I would write down Newton's law of gravitation and say, there, that's why. Newton's law explains it. Let's be a little more rigorous about what the DN model says. 2 fancy Latin-derived terms that Hempel uses. Explanandum just means the thing that is to be explained. Explanans just means the thing that does the explaining. Hempel says that there are 4 conditions that have to be met in order to have an explanation in physics. 3 of these are logical conditions, and 1 is an empirical condition. The logical conditions are: 1, the explanandum must be a logical consequence of the explanans. This means that the event has to actually follow from the law if the law is to provide an explanation for it. R2, the explanans must contain general laws and these must actually be required for the derivation of the explanandum. To be explained, there has to be an actual law that's actively used in the derivation of the observed phenomena to be explained. R3, the explanans must have empirical content. That is, it must be capable, at least in principle, of test by experiment or observation. The law of nature can't just be a definition. That explains nothing. The sort of laws that are capable of explaining occurrences must be discovered and confirmed experimentally. And then there's the empirical condition, R4. The sentences constituting the explanans must be true. This means that for a law to explain an observed phenomena, the law must be true. A false law doesn't explain anything. A legitimate physical explanation occurs when we can show that what you saw is a direct logical consequence of a true law of nature. Then the law of nature explains what you saw. That is how physics explains the world. Well, usually. Here's where the IS model is needed to complement the DN model. In physics, there are certain cases in which the laws of nature are statistical. Quantum mechanics and statistical mechanics are just two examples of fields in which statistical laws are used. In these cases, explanations will have to be slightly different. With statistical laws, the logical derivation uses a different logic, induction. Where deductive logic gives absolutely certain conclusions because the content of the conclusion is contained within the premises, with induction, the content of the conclusion outruns the content of the premises. The conclusion is a generalization larger than the information in the premise set. Therefore, we cannot have absolute certainty about the truth of the conclusion, but we can have high probability of truth. The conclusion of a good inductive argument is likely to be true. In this way, we create an inductive version of the DN model of explanation. Let's say you observe some phenomenon, call it P. If there's a true statistical law about P-type events, and you can show through an inductive argument that we should expect P to probably happen as a result of this law, then the law explains the event. So, according to Hempel, laws explain phenomena, but what explains the laws? In some cases, being able to derive them from more general laws. Kepler's laws of planetary motion, for example, can be deductively derived from Newton's laws of motion and gravitation. So, Newton's laws explain Kepler's. And what explains Newton's? Well, at some point we just have to say, this is what we found through observation. There is no more explanation. To want more is, as Russell pointed out, to look for God in the physics. So, do Hempel's accounts of explanation in physics work? This is philosophy. Of course there have been objections. One standard objection is that Hempel allows too much to count as legitimate scientific explanation. For example, for the last 40 years, I have conscientiously taken birth control pills. Never missed a day, always on time. Let us say that there's a true law that those who take birth control pills never become pregnant. You can deductively derive from this law and from the observable fact that I always take birth control pills that I am not pregnant. But if you wanted to explain why I'm not pregnant, that's really not the reason. I won't give you all the details, but I'm sure the teaching company has a course on human physiology that can fully explain it. Yet, it fits all of Hempel's requirements for a good explanation. But it evokes an objection in the other direction that's more interesting. This objection is raised by Nancy Cartwright from the London School of Economics in her amazing book, How the Laws of Physics Lie. We want physics to do two things. One, to give us truth about how the universe works, and two, explain things. Professor Cartwright points out that in Hempel's view, it's the truth of the laws that account for their explanatory power. We look for truth first, and then explanation follows as a result of the truth. Truth and explanation are not only compatible, according to Hempel, but It's the truth that yields the acceptable explanation. But she objects. Yes, she says, we do want both truth and explanation from science. But Hempel's wrong that the explanatory power comes from the truth. Indeed, he's wrong that they're even compatible. The truth, Professor Cartwright argues, does not explain much. Truth and explanation are incompatible. When we search for truth, we lose the ability to explain, and good explanations are not true explanations. Physics is at its explanatory best when it stops worrying so much about truth. The argument begins by pointing out that much of what we treat as laws of nature aren't quite really that. The example she gives is what we call Snells Law. It's the reason why a stick half in water looks bent. Now, in a standard optics textbook, Professor Cartwright finds the law initially presented early in the book in the form we usually expect. Sine theta divided by sine theta prime equals n1 over n2. Now, this just says that the angle of a light ray moving from one substance to the other will depend on the ratio of the indices of refraction of the two materials. An index of refraction is just a measure of how thick the stuff seems to light. The thicker it is, the more light will bend in coming through it. Water is thicker than air, so the bending is greater in water. This is why the stick appears to be bent when it's halfway submerged. But that's not the important part. The important part is that Snell's law appears again 500 pages later, but now it's the refined version of Snell's law. The refinement limits the applicability of the law to optically isotropic media. That is, light moves through in the same way regardless of direction. And you guessed it, in the real world, most media are not really optically isotropic. They are more or less isotropic in a way that makes Snell's law a good working approximation of the actual, much more complex reality. The law is not a law. It's not literally true of almost anything. And this is the case, Professor Cartwright points out, in general. There are no simple relations describable by straightforward equations in reality. The world is messier than our clean theories lead us to believe. The supposed laws only hold in perfect circumstances. The Latin phrase is ceteris paribus, which translates to all other things being equal. But in reality, all other things are never equal. Our best laws of physics are not true. They are at best true-ish. Funny, you don't look true-ish. We do work hard to correct them. Physics does try and try and try again to make the laws true by constantly adding corrective elements, by including additional factors, by making the equations as complicated and messy as the world they're meant to account for. But in making our laws more true, what we also do is make them less explanatory. The better explanations are given by the ceteris paribus laws. So if you ask me, Steve, why does this stick look bent when I stick it partway into the water? The best explanation comes from my explaining Snell's law to you, even though I full well know the law is not actually true. But it's true enough to give the best explanation. Science has conflicting goals in seeking truth and seeking to explain. We have to neglect one when we work for the other. Science, when it seeks to explain, is like theater, Professor Cartwright argues. Good theater can express human truth, but it does it by creating characters who embody human qualities, but are not deep and round, who don't have complete lives, who lack the full complexity of true humanity. But they represent it well enough to be able to say something deep. We leave good theater thinking we've learned something about the human condition. In the same way, Professor Cartwright argues, we leave good physical explanations thinking we've learned something about the universe, even though we learned it from a model, from a simulacrum, from a simplification. So, does physics actually explain anything? If so, are these explanations true? Interesting arguments pull us in different directions. Don't you just love philosophy?